The first type of equation we're going to look at that is solvable via substitution is going to be the homogeneous equations. Let's suppose that we have a function f that possesses the following property. If we replace the variables x and y with tx and ty, if the result is t raised to some power times the original function f of x comma y for some real number alpha, then f is said to be homogeneous of degree alpha. For example, if we looked at the function f of x comma y, which is equal to x cubed plus y cubed, this would be a homogeneous function of degree 3. And in order to see that, what you would simply do is to test, you would replace x with t of x and simultaneously y with t of y. You would substitute it into the equation. You would try to see if there's a common factor of t that you could pull out. Here, of course, we can pull out a t cubed. And by factoring that out, what we're left with is t cubed times x cubed plus y cubed, which was the original function. So this function would be homogeneous of degree 3. However, if we just tweak this one a little bit, if you had the function x cubed plus y cubed plus 1, then this would not be homogeneous. In particular, having that constant of 1 there would kind of prevent that from working. You would try the same test. You'd plug in t of x for x, t of y for y. You would get t cubed x cubed plus t cubed y cubed, but the plus 1 would not have any power of t with it, so we would not be able to factor out a t, any common power of t, and recover the original function. Okay. If a differential equation is homogeneous, then what that means is that the coefficient functions m of x comma y and n of x comma y are both homogeneous and of the same degree. Okay, so to be very careful here. We know what it means for a function of two variables to be homogeneous. We just defined it above. This is a definition about a first order DE being homogeneous. And what that it means is that both of its component functions are homogeneous, and furthermore, they both have to be homogeneous of the same degree. So if m is homogeneous of, let's say, degree 4, and n also happens to be homogeneous of degree 4, then we would say that our differential equation itself would be homogeneous of degree 4. Okay? And one of the things that's going to be nice is that if we have a homogeneous equation, we can actually turn it into a separable ODE via a substitution. Okay? So let's suppose we have a homogeneous ordinary differential equation. So we know that m and n both satisfy this kind of relationship for some alpha. They're homogeneous of degree alpha. Let's see how we can turn this into a differential equation via separation of variables. So first thing we want to look at, so let's just focus on m for a moment. Okay, let's suppose that m is homogeneous of degree alpha. Then what we know is that m of tx and ty is equal to t alpha times m of x comma y. And let's make the following substitution. Let's let, well, maybe not a substitution, but let's let t equal to 1 over x. Okay. And let's see what that would give us. If I replace t with x, I'm going to get 1 over x times x, comma, 1 over x times y. This will be equal to 1 over x raised to the alpha times m of x comma y. Well, 1 over x times x, that's going to be 1. We can write this 1 over x times y is the same thing as y over x. this part here, when you raise a fraction to a power, raise both numerator and denominator to that power. This is 1 over x to the alpha, m of x comma y. And then I'm going to solve this for x comma y by simply multiplying both sides by x to the alpha. So multiply both sides by x to the alpha. Here's what we get. We have x to the alpha, m of 1 y of x, or over x, is going to be equal to, these cancel, m of x comma y. Okay. Furthermore, the exact same work. So if this differential equation is homogeneous of degree alpha, then we can get an equivalent expression for the coefficient function n. It's also true that n of x comma y is going to be equal to x to the alpha times n of 1 of y over x. Okay. And now what we're going to do is we're going to make a substitution here, and this is the substitution. Let's let u equal y over x. Okay. So this is going to be written as x to the alpha, m of 1 comma u. This is going to be equal to x to the alpha n of 1 comma u. And we're going to take that and plug that into our original differential equation. Everywhere I see an m of x comma y, I can replace it with x to the alpha m of 1 comma u dx, plus everywhere I see an n of x comma y, I can replace that with an x to the alpha n of 1 comma u dy equals to 0. We can get rid of the x to the alpha by simply dividing the entire equation by it. So let's divide by x to the alpha, divide by x to the alpha. And right now, here's what we have. We have m of 1 comma u dx plus n of 1 comma u dy equals to 0. So this was our substitution. This is very important. So we let u be equal to y over x. Or if we solve this for y, multiply both sides by x, we have that y is equal to x times u. Maybe I'll write the u first. We'll call it u times x. Doesn't matter, same thing. But now I can calculate dy for this. So if you wanted to take the differential, so what would dy be equal to? Well, this is good old school product rule. It'd be the differential of u times x, that's x du, plus u times the differential of x, which is u dx. So in our differential equation, where we're at right now, everywhere we see dy, we can put this. So let's come over here and do this. We have m of 1 comma u dx plus n of 1 of u times dy, which dy is this expression here. It's x du plus u dx equals to 0. So this is where we're at right now. And this should make us happy. All of you should be asking the question, well, how in the world does this make us happy? The answer is that this differential equation, so what we have done, under this substitution, this thing is actually separable. We can get our dx terms on one, our dx and our x terms on one side, and our u and our du terms on the other side. Let's simply go ahead and distribute the n of 1 comma u through. We're going to have n of 1 comma u x du plus n of 1 u times u dx equals to 0. I can get these two things together and factor out the dx. So I'm going to have m of 1 comma u plus n of 1 comma u with a dx. I'm going to bring this term to the other side of the differential equation. Let's call this minus n of 1 comma u x dx. And now here's what we're going to do. I have a dx on this side. Whoops, wait a minute. That's not good. Blah, blah, blah. Copy mistake. No, we do have a dx on that side. I copied this wrong, over wrong. This should be, right, I said I was taking this term to the other side. That should be a negative n1u x du. So I want all of my x terms on the left side and all of my u terms on the right side. I can divide by this quantity. I can divide by m of 1u plus n of 1u to both sides. And I want to get rid of this x that's over here, so I'm going to simultaneously divide both sides by x. And so in its nitty-gritty form, this is what we end up with. This and this cancel, so we get dx over x equals, over here, the x's cancel, I get a negative n over 1u divided by m of 1u plus n of 1u du. And it might not have been at all obvious why we cared so much about this form, but notice these three terms. When you have something like, let's say, m of 1 comma u, this is essentially, this is a constant, so this really just gives us m as a function of u. So these coefficients on this right-hand side are all just functions of u, and therefore this thing can be solved by integrating both sides. This is going to be a function of u du, we can integrate, and obviously we can integrate 1 over x dx, and so this is going to give us what it means to solve this kind of differential equation. And then the idea is that you can solve this for u. So we want to solve this differential equation. This one here, we want to solve it for u. Again, so let's suppose that there is a solution. Let's say that u of x is equal to psi of x. Then the solution to our overall differential equation would simply be y equals psi of x times x. And that would be a solution to our starting differential equation. Whew, all right. Hopefully that all sinks in after some point in time. The moral of the story is this. So what do you want to take away from this? The idea is, first of all, we want to be able to check to see whether or not a differential equation is homogeneous. That should be straightforward and pretty easy to do. Once you recognize a differential equation is homogeneous, then it can be solved using the substitution y equals ux. You calculate dy, you get this expression. You will end up with a separable differential equation in the variables x and u. Solve it for u by separating and integrating and solving for u. And then the solution to our differential equation is going to be y equals that solution function u times x.